Oh, hello everyone. Welcome to another Codeforces stream. I guess it's been a while. Yeah, I guess like 2 weeks ago or 4 weeks ago I went on vacation for 2 weeks and I thought I'd come back really refreshed and just like stream all the time. But then I guess that didn't really happen. So, but I figured I'd do a Codeforces. I thought it'd be fun to do in this Thursday. It's just about to start, I think. Where are we? Just 3 minutes. Yeah, there were some delays. I couldn't find my tea strainer, and I wanted to make some green tea to have like while I was streaming, but I had to make coffee instead, which might be an upgrade, so it's all good. I wonder if I can get sponsored by my local coffee shop. Probably not, but maybe I get sponsored by Starbucks. Or no, Red Bull sponsors like all kinds of people, right? Maybe that's who we should hit up. Let's see. Another delay was oh yes, yeah. Error while starting the webcam. Comment to do useful message. Sort of funny. Yeah, I guess this script I just like copied off the internet, so I shouldn't be too surprised it doesn't really work that well. There's this thing called v4 L2 loopback, which I randomly have to reinstall all the time to get it to work, but I guess it's all worth it to have this high quality GoPro view of myself. Let's see, we got almost 24,000 today. I wonder if we'll hit 24,000. And just a 2-minute contest, which I like. Sometimes they're 2 hours and 15 minutes. I don't really want that last 15 minutes. I feel like 2 hours is a nice, clean, round amount of time. Very optimal. Very, very optimal. Oh, hey, OsJam99. How's it going? Oh, you got a cool emoji. What is that? A GLHF pledge. Nice. So are you Australian? Is that why your name is OsJam? Congrats on your bronze place finish. I actually thought that so like Australia was obviously the favorite going in, and the prediction markets had them at like 98% to win essentially, because you could bet on whether Ledecky would win 3 gold medals. And I was like, obviously they're not 98% to win, so I put a lot on the 2%. And then America did beat Australia, but they lost to China, so it was very sad. Oh yeah, I guess there's probably more people named Austin than Australians, right? Or actually, that can't be true. There aren't like millions of people named Austin, right? But probably I should think someone who comes to my stream is more likely to be named Austin than from Australia if they put Austin name. I guess because it'd just be kind of weird to be Australian and then advertise in your username. Are you going to do the contest, OsJam, or just hopping in? Let's see. Yeah, I'm probably super out of practice. I don't think I've programmed at all for 4 weeks. So we'll see how we do. Let's. Got my coffee. 10 seconds. Yeah. Oh, hi, Cassinigrade. Yeah, it has been a while since I've done competitive programming. I'm sure you're all waiting with bated breath for the next installment of high dimensional probability, which I should probably get back to as well. Okay, so cherry. So we have n integers, and we want to find the maximum value times the minimum over all pairs LR of integers. Wait, this problem doesn't sound trivial. They're always trivial. Okay. Oh, okay. Over. Okay, so we want to find them. We have a sequence, and for all subsequences, we want to. Okay, and then the length is up to 10 to the 5th, so we do need a linear time algorithm. Okay. Maybe. Okay. I see. So there's quadratically many pairs, but we don't compute all of them. We want to find the one which is maximized. Okay. So the answer will always be the maximum value in the sequence squared. Because if L equal, oh, but L has to be strictly less than R. Okay. Well, still, we only have to consider sequences of with 2. Or do we have to? I think with 2 things we'll always achieve the maximum. Okay. Okay, so we got T inputs, and then we need to read in N, and then the sequence. Okay. So N equals. I should have typed out N. So we got N, and then we got the line, which is that. Okay. Just make sure that's right. Okay. Yeah, it looks like it's putting out the right lines. Okay, and then I think we just only look at length 2 things. So for I in range, so I guess N minus 1. The answer equals 0. Answer equals the maximum of the answer we already have, and the max of our value at I and I plus 1 times the min of those things. Oh, oops. I want to just copy that. Okay, and then let's just print the answer. Oh, and stop printing outline. So we get 12, 6, 4, 7, 6, 1, and this other number that's quite big. Okay, do we have to worry about... okay, the numbers are bounded by 10 to the 6. I don't think we have to worry about overflow. Yeah, why do I think just looking at 2 is optimal? Yeah, so you'll all... I don't know. I'm convinced it is optimal, though. Let's submit. Okay. Oh, where am I? I always forget to pre-do this to save time. We're in competitions, Codeforces, R735A. Really, it has to be optimal, because if it's not optimal, then it's a really hard problem. And it can't be a really hard problem because it's A. Okay, long queue. I'll start reading B. I guess there's no reason to sit here refreshing. Okay, Cobb. Yeah, we are in div 2, not div 1, so it should be an easy problem. Okay, so now, again, we have n integers and an integer k, and we want to find the maximum of I times j minus k times... Wait, what's this operation? Oh, the bitwise XOR of the values at I and j over all pairs ij of integers. Okay. Interesting. Just double check that worked. Wow, still in the queue? Okay. Okay, so again, I is strictly less than j, which I guess makes sense because the bitwise OR of something with itself is itself again. Okay, so yeah, and it's so in the previous one it was sort of symmetric over I and like the indices I and j, but here there's sort of a bias where we're gonna want to pick things towards the end. What is and k is a given integer. Okay, and k is less than 100, and I guess also less than n. Okay. Oh, okay. And so the previous one we like were looking at the subsequence, but here we only care about like the two values at AI and at I and J. Oh, how's it still in the queue? Okay. Okay. Oh, so this is bitwise OR. So yeah, let's make some observations. So we have for two numbers A and B, the bitwise OR is greater than A and B. I don't know if that'll help us. So the answer is always going to be less than or equal to n times n minus 1 because the answer is like the maximum of I times j, and I and j are less than n and n minus 1. Okay, so the integers are not necessarily positive, but they are non-negative. Okay. And I guess k is sort of a bias away from the end. Okay, the integers themselves are small. No integer is larger than n. So I guess that's sort of important. So we know that a or b is less than or equal to 2 times the maximum of ab. And so this is less than or equal to 2 times n. So that means the answer should be greater than or equal to n times n minus 1 minus 2kn. Yeah, this sort of means that you don't have to check that many things. Let's see. So this is equal to n times n minus 1 minus 2k. So that means that okay, so and then if you check, so this is a lower bound on what you'll get if you just check the last two things. And what this means is if if I times j is less than this, then you don't have to check it. Okay, so that means like for n, you only have to check the 2k things. For n minus 1, you only have to check 2k things. So you really only have to check I guess 2k squared pairs. And we can just do that because k is less than 100. So, okay, so we have a quadratic algorithm, but it's not quadratic in n, it's quadratic in 100. So that's totally fine. What? Okay. I guess Codeforces is having some issues here. The stream looks fine, so it shouldn't be my internet. I guess 30,000 people is too many. Well, we know the problem. We can start coding it up. I just wanted to check if we actually did get A before we went too far, but yeah, maybe I should have some like habit of like curling all the problems so I have them locally in case this happens, but I don't know. This is actually the first time I think I've seen Codeforces like literally go down, but it's not really an issue since we already know the problem statement. Okay, so we so we are I assume we're given line or n to start, so we just copy and paste that. So that's on line 15. And then we're given the same format line, so I'll get that as well. Click out of that. Okay. Okay, so now for I in range 2k, for j in range 2k, there. I guess 2 times k. I've been doing too much math. Juxtaposition should be like legal though. You should be able to write like 2k for 2 times k. You could do that if I wrote a programming language. Though maybe that messes with the variable names, because I guess you want to name your variables like k2 but I don't know, who puts their coefficients at the end anyway? Okay, so let's see, answer equals 0. And then, so these are our okay, let me just, let's start at n, go to n minus 2 times k, and just take the minimum, or sorry, the maximum with, oh wait, no, I don't want to, oh yeah, it's the maximum with 1. And we're stepping backwards. And let's have j go from, it should start at I minus 1. Okay, and the start is inclusive even when you're stepping backwards. Oh, and the back one is not inclusive, so I should actually stop that at 0. And we want to go down from I all the way to, I guess the same place. Stepping backwards. And I think this is fine. I should make this -1. So of course I can never be 0 because my I is greater than my j. So that's fine. Okay, now we just compute the thing. So answer equals the maximum of answer and I times j minus, it was just k, right? K times, and then the bitwise OR of the value. Why did I call it line? I should call it A or something. That would be more optimal. Okay, and then we just print the answer. Okay, and I think that should be correct, but hopefully, oh, okay. Let's see if Codeforces is back. We'll refresh. Okay, it's back, cool. No problem at all. Wait, what the heck? What's the input? The input gives us k. The input gives us k. Right. So let me just yank this. So nk. List index out of range. Okay, so I thought I had this set up so we wouldn't get too small, but perhaps I was wrong. Let's just print out what they're looking like. Print ij. Oh, what the heck? I don't know what I clicked. Okay. So what am I printing? Did I I printed 3, 2. Okay, so it started with 3, 2. Oh, okay. We don't actually want to start at n. We want to start at... Oh, right. I mixed up my inclusion because somehow it feels like the larger one should not be included, but that's not how it works. The first one's what's not included. Okay, now we're printing numbers. Let's get rid of our IJ. 0006. Those seem incorrect. Oh, it is allowed to be negative. Oh, I see. So I need to let answer be very small. So what is the smallest possible answer? This is less than 2 times n, so negative 2kn is smaller than the smallest possible answer, so I'll just let that be my initial answer. We get negative 3, negative 6. Okay, so still wrong. Repeating the right thing, right? I times j minus k times the bitwise OR. Do I have my k? Yeah, I do have my k. Okay, so Oh, you know what? I think the problem is indexing. So actually, this should be I plus 1 times j plus 1. Negative 1, negative 4, 3, 12. Okay. So, I guess one concern is I did not actually test it. I did not test this logic where I stop at the bottom anywhere. So, like, I guess there is some concern that maybe I implemented that part incorrectly. Oh, thanks, Nick Polaris16. Of course I want to become famous. I feel like there should be like better Twitch spam detection. But maybe it's just a hard problem. People just add weird punctuation and stuff and hide the URLs. Okay, so I'm confident that I'm checking everything I need to check because it'll get too small at this point, and yeah, it'll stop at that point. Yeah, okay, let's just submit. But before we submit, let's see if our last one was accepted, because I guess we still haven't seen that. My submissions. Okay, pretest passed. Okay, let's submit B then. Okay, yeah, worked on the last run. I haven't changed anything. Oh, wait. It's been changed? How's it been changed? Oh, okay. I guess there was some error in there. Yeah. I don't think that should affect us though. Submit B. Of course, I have to stand here refreshing for a second. I should probably just move on again. I guess their website's not being too fast today. Okay, let's see what Mikasa is about. Mikasa. So we have two integers, n and m, and we want to find the mex of the sequence n bitwise XOR 0 and bitwise XOR 1. Okay, and what is the mex? The mex is of a sequence of non-negative integers, the smallest non-negative integer that doesn't appear in the sequence. Okay. I wonder if they try to correct this and that's why things crashed. Okay. Still in the queue. Yeah, their queue's slow today, so there's a lot of people doing this one. Okay, so yeah, I think I understand the concept of a mex, and now we have n and m, and okay, so we have m integers, so m is potentially quite large, so we can't just, okay, but this is going to be a very normal kind of sequence, I guess. So what's going to look like in general? So the first is always n, because the bitwise XOR like 0 is the identity. This is a group. So the first one's always n. This one's always, it's sort of like n plus minus 1, I guess. So depending on whether the last digit is 1 or 0, this will be n plus minus 1. The second one will be like n plus minus 2. The third one will be n plus minus 1 plus minus 2. Okay. Interesting. So if m is smaller than n, then this sequence will never contain 0. Yeah. So, yeah. Let's do an example. I kind of think these things are going to look very regular. Let's try to find the trick. I think an example. I'll list it. What's going on? So let's say our number is all ones, so it's like 4 ones, and then our m is smaller, it's like 3. So yeah, m less than n, or answer equals 0. Okay, and then so here our number is 15, and we have to compute 7 numbers to find it. Oh shit, I got wrong answer in the second question. I mean, thanks for letting me know. Thanks for monitoring. Wrong answer on pretest 3. Okay, I guess I should figure that out first. Okay. Okay, so where could we go wrong? So somehow we must not be going deep enough then. So if I times j is less than or equal to, okay, so what was my logic? My logic is the bitwise OR of 2 numbers is bounded above by 2 times the maximum of those 2 numbers. Let's double check that. Yeah, I think so. The bitwise OR is bounded above by the sum of the numbers, because if you've got some like bitwise representation and some other bitwise representation, all you're doing is, so if it was the case that they only had ones where the other had zeros and vice versa, then these would actually be equal. But then when there's actually 2 ones at the same time, you don't add this. So this is an upper bound, and then of course a plus b is less than or equal to 2 times the max of a times b. So we definitely have this property. And then the numbers are less than n. That was given in the problem statement, right? Yes, they're less than n. So yeah, so this definitely holds. Now, what is the answer greater than? So the answer is definitely greater than, so the answer is a max over all pairs, so it must be greater than what you'd get if you did it at the end. And if you do it at the end, what do you get? You get n times n minus 1 minus something that is minus something. So, and then if you make this something larger, then that's an upper bound. So this is like x, the OR times k. So this is definitely a lower bound. And then I factored out this. And then what did I conclude from that? So if for any pair, the number you get is going to be less than or equal to just multiplying them. So if I times j is greater than or equal to this, then we're good. I should probably think carefully, but let's actually think here. So I probably just am not going deep enough. So I only go to n minus, oh yeah, and it won't even include the last one. So So I need to include this, but I actually also need to include this minus 1. Let me just be extra sure. And then I don't think I've copied and pasted anything else. So it won't change the answers, which is the problem. So I probably shouldn't just go ahead and submit. I guess like a counterexample would be one that like forces me to choose the last possible ij, where like those are as large as n. So like at this entry it's as large as n, at these two it's as large as n, and everywhere else it's 0. Or no, at these two it's 0 and everywhere else it's as large as n. I guess that would maybe do it, but I think it's clear that I wasn't going back far enough. Because yeah, I'm just going to resubmit. I guess another place I could have an error is it's possible that this isn't the minimum possible answer, but I believe it should be the minimum possible answer, because yeah, like the XOR can be no larger than 2n, and then multiplied by k, and then yeah, so it should be for sure smaller than the smallest answer. Okay, there it passed. Okay, I off by 1 errors. Killer. Sort of annoying. I should have just given myself more leeway. Nice AC. Or is AC slang for accepted, or? Okay. So we were doing this one, and oh yeah, I was just gonna work through an example to get a little bit of insight. So we'd go from 0 all the way up to there, inclusive, I guess. So yeah, we do start at 0 and we do go all the way to n inclusive. And what would the bitwise XOR look like? So the first one will, of course, wait, heck, something's wrong with this. Oh, there we go. Okay, so the first one will always be the same. So yeah, and then the second one will be that plus or minus 1, depending on whether there's a 0 there. I hope maybe this isn't the best example. So yeah, I guess in this example, it's just like kind of purely counting down from the number we had. So it's just counting down, and oh wait a minute, I think I'm backwards here. So if m is less than n, yeah, oh yeah, so if m is less than n, the answer will always be 0. So actually the interesting case is always m is greater than n. So yeah, this one of course is going to equal 0 for trivial reasons. Okay, so what happens then? So as we go from 0 to n, we'll get every number from 0 to n. Yeah, and then at n is where things start getting interesting. So I guess at n we start counting back up. And so what is n bitwise or n plus 1? Is this like no, I guess this actually is sort of like a complicated thing, which depends on what n is, because like so if n mod 2 equals 0, then this is just going to equal 1, because this will just change the last bit. But in the other cases, it can be like much more complicated. So like this will equal like n plus like 2 to the k, or like if n is all ones. Because then adding 1 just makes all these 0 and has a 1 there, and then it's just like a much bigger number. And it's actually not true that we're going to get every number from 0 to n as we count from 0 to n. So we're definitely going to get numbers that are larger than n. Because if n is 1, 0, for instance, then as you count, you start at 0, you get 1, 0. You start at 1, here you get a number that's actually larger than n. And then n equals m, and you get 0 again. But of course, we didn't count off every number between 0 and m. We missed 1. So here the answer would be 1. And then we would get 1 when we went past it to like 11. It's sort of a more complicated problem than I thought. Okay, so I wonder if we should ask some question like if we should if we should start by asking something like, will 2 to the k be possible? And we can like start at we could start at like k much larger, or k larger than log n, and kind of go down. So like if k is larger than log n, or I guess we shouldn't start at log n, we should start at like the max of log n and log m. I wonder if this is a fruitful approach. So in some example where like n equals 1, 0, 0, 1, m equals, so a larger than nm is the interesting one. So let's just go all the way up. So of course, yeah, I guess actually we should be looking for numbers that we can't achieve, not numbers that we can achieve. So if like we find that maybe we should just do more examples. So I already tried doing examples. Okay, so I guess I did this example where n was all ones, and this example is sort of maybe silly because as you count up, you just count down. So it's sort of, yeah, it's just the same thing as n minus m. Yeah, because Yeah. So n XOR m equals n minus m if n is all ones and greater than m. Yeah, so in this case, we know we'll achieve everything from 0 to n, and then once we get to m equals n plus 1, then it starts getting interesting. Yeah. But actually, even that case is already sort of interesting. Maybe we should work out what happens there. So let's say we get to all ones. So then here we've got 0, and then the next one, now the bitwise OR is quite large. Yeah, so once we get to this point, all the smallest number we haven't visited is m itself. Or sorry, is n plus 1. Yeah. Okay, so in all one's case, go from 0 to n, then n plus 1 is smallest unseen. So what would you have to do to see it? You'd have to get all the way to the next all ones vector. To see it, have to go to next all ones. Hey Kevin, how's it going? Yeah, so then when you get to the next all ones vector, you'll see n plus 1. And at this point, what is the smallest vector, or the smallest number you haven't seen? I guess you'll have seen every vector, or I keep saying vector, I guess I'm thinking of them as bit strings at this point, but you'll have seen every number up until this all ones vector plus 1. Yeah, because once you get here, now you're kind of doing the same thing again, where you just added this extra significant digit. So here you counted from n to 0, and now you counted from n with this extra 1 down to 0 plus this extra 1, and now the smallest vector you haven't seen is the one with 5 trailing zeros. Okay, so I guess so if n equals 2 to the k minus 1, the answer should equal some number of ones appended with some number of zeros plus 1. Where the number of zeros should be k minus 1, and the number of ones should be log base 2 of m minus k minus 1 or something. It might be off by 1. I'd have to double check, but I think roughly this. Yeah, all that matters is kind of the rough order of magnitude of m. But what happens if m is not all ones. So yeah, this is sort of a toy case, which maybe isn't capturing everything. So what happens if n is some like very complicated number, 1 1 0 1 1? So you still have to go up to at least n, or answer will equal 0, because this is the first one where when you XOR with you get 0. But so in the all ones case, the special thing is after you've gone up to n, you've seen every number between 0 and n. But in this case, even once you get to n, you haven't seen every number between 0 and n. You haven't seen... so the smallest number you haven't seen should be the number that has a 1 here and zeros here. Because you need to see I guess the all ones vector to get there. Okay. I think I'm getting the idea. So let 2 to the k minus 1 be the smallest number of that form, greater than or equal to n. So basically just the smallest all ones vector that is greater than n. So every time n makes a step of this size, you will have seen every permutation of the last. So every time n makes a step of this size, we'll see every combination of trailing digits. So let big N equal log base 2 of n. So this is a floor. So this is the number of, or maybe, no, I think I want ceiling. So if n is 3, then this would be 1, but I want it to be 2. I want it to be the number of digits in the representation. Wait, is this right? I mean, so if n is 4, then this would be, maybe I need like a +1. So log base 2 of n plus 1. Maybe floor plus 1. Yeah, floor plus 1. Number of digits. Yeah, so if n is 4, then this is 2 plus 1, so 3 digits. If n is 3, then this is floored, it's 1, so 2 digits. Okay, checks out. Okay, so every time n makes a step of size, so now this is the same thing as 2 to the n minus 1. So if you, yeah, so if n is, I guess it should be, yeah, so if n is 4, this is 2 plus 1, 3 digits, so now 2, 3, 8 minus 1, so 7, which is 3 ones. Okay, so every time m makes a step of this size, what size do I mean? I mean size, I'll give this one a name too. I'll call it m. Size m. We'll see every combination of trailing digits, trailing n digits. Okay, so okay, so M will have n digits back here. So it's trailing n digits and leading digits. Oh, and I shouldn't. Here I mean little m. I shouldn't. Maybe not have called this one big M. Okay, so if this is our M, we'll make a step of size M this many times, like leading digits times, and then for the last one we'll have some other stuff. Okay, so let's break up M. Let's call it M1 and M2. Or I kind of mean these as strings. So once we get to M1 plus 0, or here I guess I mean M1 as a number. So once we get to M1 plus 0, the answer is going to equal it's going to equal M1 plus N plus 1 will be the smallest number we haven't seen yet. No. No, the smallest number. So let's say once we get to M1 plus 0, not inclusive. Or do I want to? Yeah, so we're cycling through these trailing n digits, and we see we XOR with n, and we see every combination from 0 to n, and then we do the next one. So if this was 0, the answer is n plus 1. Oh, okay, and then we do it again, and we've seen so like we get a 1 here, and we've seen every combination here. But we haven't seen it plus 1. So yeah, this is the answer up to this point. Okay. But now we need to do like the trailing bit. So we get so we have some M2 and some N. And we want to find the smallest thing that we don't see. So we have M2 and N. Want to find smallest N XOR L, where L is less than or equal to M2. Okay, so I guess we just need to find what we can kill. So if n's digits look like x1 up to xn, then we just need to find which digits we can kill. So if so we can just go and like forwards to backwards, and like if m2 is greater than or equal to 2 to the n, then L equals 1, and then other digits, and so on. Okay. I think this should work. Let's code it up. Okay, here we go. Okay, so I want to open C. What do we have? We've got what's the input look like? So we have T, and then we get just N and M. Okay. Let's just copy that line. Okay, why am I tab editing things? Okay, C. And then there's no more line. And I want to call it NM. Okay, so we need to make an algorithm. Okay, so leading digits should equal, all right, let's define n first. So n should be log base 2 of n plus 1. I feel like there's some very nice way to compute log base 2, like using a bitwise operation instead of this, but whatever, it works. And I probably need to floor this. I hope this works. I feel like at some point Python was like, no, you can't just take the integer of a float, I'll complain, but I'm sure it'll work. Or maybe you can't take the integer of a string that encodes a float. You have to like first make it a double then. Okay, so that's n. And now let's compute the leading digits and the trailing digits. So the leading digits, or let's do trailing first, and I'll call it M2, the monetary supply. So it should be, what should it be? It should be 1 bit shifted by n minus 1. Bit shifted by n plus 1 probably. Yeah. Right, because 2 to the 1 is 2, but if n is 1, or actually, no, it probably should not be plus 1. Yeah, if n is 1 digit, then 1, yeah, okay. And I want minus 1, of course. Okay, so, oh, yeah, so that's the all ones vector, and then I want to and it with m. And then what should M1? M1 is just M minus M2. Okay, let's just make sure we're doing this computation correctly. Just hide this real quick. I have it always on top, but I guess I could just toggle it. I don't know. So let's just give it one case. So n doesn't matter. What's an interesting m to c? Oh no, n does matter because it determines what the threshold is. So let's make n 4, and then so the trailing digits will be the last 3, and the leading digits will be the first 3. So I just let's make it like I don't want to do too large of a number. Let's do 17. Right, yeah, and this is correct. Okay, so it's probably correct for all numbers. Okay. So So the answer is going to have leading digits M2 or M1. And then the question is just what trailing digits we miss. So right, so it's just like there's some like very nice way to compute this. Can I just maybe there's not. So I want to just kill as many digits of n as I can. So if M2 is large enough to get to this leading digit I want it to, and so on. Okay, so, and I guess n is always going to have a, okay, so, let's call it trailing answer equals 0. So while, let's say for I in range, so I just want to start with the first leading digit. So n has n digits, so I'll start at n, and for each digit I'll see if it's included. I'll go down to 0, or I guess 1. Going backwards, and I just want to ask if it's possible to include this digit. So if trailing answer plus 1 bit shifted by I, so if I'm on, if n is like just, oh wait, this should be 0. I do want to include 1. Okay, so bit shifted by I. So if this is less than or equal to M2, because that's what I can't exceed, then I'll just add it. And then my answer is M1 plus my trailing answer. Let's see if that works. Got some numbers. 462? Oh. No, it doesn't quite work. Let's print out some in-between things. Probably there's like off by 1 errors here, like galore. Oh, do I want to go to 0? So let me think. Do I want to go to 0? So the first, so n has n digits. The first number I want to consider to add is the number that has a 1 in that digit and 0 everywhere else. So like if n has 1 digit, then, oh wait, this should actually be I minus 1, I think. Or should it be I minus 1? Or maybe I should start with n minus 1 actually. Yeah, because shifting over by n digits is the number that's greater than it. Okay, and then so I actually want to go to 0 inclusive. Change anything? Did not. Just suspicious. Oh wait, no, it changed the first answer. So now we're extra wrong. Let's see. Let's try to understand the first case and why we're getting it. Or wait, so let's understand the one that's 0 actually. Why are we getting this one wrong? So here it's 3, n is 3, m is 2. Okay, so do I need like just some if statement? Like, will my algorithm even work for it when m is oh, maybe I'm just like solving the wrong problem actually, because we want to find we want to find the smallest number we don't get to, but here I'm kind of finding the largest number. So yeah. So I guess we want to find like the things we can't kill. Yeah. I think it's just like sort of wrong thinking. So we want to find oh, okay. So maybe I just didn't code up what I meant. So we want to find the smallest n XOR L. Okay, so here we kill what we can kill. So yeah, we want to kill all the largest digits. So instead of adding the trailing answer, I want to add the trailing answer XORed with n, I believe. Six, 2, 1. Interesting. I'm trying to think if there's like some systematic way I'm off. I guess I'm not actually. So, well, 6, or maybe. Well, I was gonna say maybe I'm off by being XORed with 1 in all these cases, but I guess that's not quite right. Okay, so why is my answer not working for 3, 2? What happens in 3, 2? Where's my pen? Oh, here's. So 3, 2. It looks like this and this. So there are no trailing digits, only leading digits. And we want to see what can we kill? I can't. So n is fixed and n is ticking up, and it's what we're like not getting to. So yeah, maybe this is sort of backwards. So we and so how could we get to 0? We so we can't get to 0. Oh, wait. So we can't get to 0 if m2 is less than n. So the only way you can get 0 is if m2 equals n. And then at that point, it's like a question of what we missed. And we want to find the smallest number that we can't kill. Okay. Okay, so let's say like n is now n1 to nn, and m is m1 to mn. We want to get the smallest number we can't get to. So let's say So m2 is greater than or equal to n. So we can get to 0. But what numbers can we not get to? Okay, so if m2 is greater than or equal to n, then we can kill every, we want to have, so I want to choose L, which has a 1 everywhere n does. But we can't necessarily do that. Oh, okay. So I don't just want to blindly add like this digit if it's like permissible. I only want to add it if it's a 1 in n. Let me give one push I a name. Call it at. Okay, I'll just leave the parentheses. Why not? So I can't add at if it's larger than m2, but I also only want to add it if it's in n. So, and at, I guess, so at and n does not equal 0. Let's see if that works. 601, 704. Oh, okay. No. Does not work. Wait, so let's look at the instructive example again. Okay, so I feel like I'm thinking about this very backwards actually, because this is just like not correct at all. Okay, so I should just work out like a table and look for patterns. Okay, so at m equals n, or m2 equals n, have we, so we've gotten 0 at this point, but have we gotten 1? I guess yes, if n mod 2 equals 1. Yeah, so if n mod 2 equals 1, then n minus 1 is what XORs to 1 with some number. Have we gotten 2? Yes, if n mod, or I guess not mod, n and 1 0 equals 1 0. Because if n mod 1 0 equals 1 0, then okay. So this, yeah, and I guess this pattern can. I was hoping the pattern continues, but I guess after 2, the numbers stop having only exactly one unique one of them. So have we gotten 3? Yes, if n XOR 3 equals 3. But if this is true, then in fact we've already gotten 1. So I think okay. I think I see it now. So like the trailing answer should equal the smallest smallest 2 to the k with 2 to the k XOR n equals 0. And then or it equals 0, or sorry, so with it not equal to 0. Or like this isn't right. Is it? Okay, so we want the smallest number. So have we gotten 1? We have gotten 1 if 1 XOR n equals 1, because n minus 1 we've already seen. Have we gotten that's too big. Okay, so I guess actually we shouldn't start with the question, have we gotten... Oh, I was going to say we should start with the question, have we gotten 0? Okay, but we always get 0 once we get up to n. Have we gotten 1? We will have gotten 1. Oh, I guess this is the right answer. Yeah, because so in the case when n is all 1s, then this is just the right answer. Oh yeah, so n, yes. So yeah, so will we have gotten 1? So we'll always have gotten 0 at this point. How will we have gotten 1? We will if the first digit is 1, because then n minus 1 XOR it is equal to it. Otherwise we won't, because n plus 1 will be the digit. Will we have gotten... yeah, and will we have gotten 2? Yes, if it doesn't have a 1 in the second digit, because then n minus 2 XOR with it gives you 2, and so on. So so at this point, the trailing answer will be the smallest 2k that... this should be an and. That isn't in... Yes, that isn't in it. So that equals 0. So at this point, this is the answer. So now the question becomes, when we keep going, okay, so then we keep going. We go to like m2 plus 1, m2 plus 2. And what would cause this to no longer be the answer if we get to n plus 2k, this is no longer the answer, because we at that point we'll have seen 2k. So the trailing answer will equal the smallest 2k that's not in n, and so not in n, and such that n n plus 2k is greater than m2, strictly greater. So we haven't gotten to it yet. Okay. So we should start from where's my terminal? Oh, I put this always on top, right? Okay, so we should actually not start at the end. We should start at the beginning. We should go up to n. And we shouldn't include n. And where are we at? We start at 1. And what is our condition? So we want at to not be in n. So what does it mean to not be in n? It means that you do equal 0. And what do we want? We want at plus M2 to be wait, is this our condition? Something about this seems weird. So we want to get to n plus 2k, and we get to it if m2 is... We want to not get to 2k, and we do not get to it if m2 is too small. So we want m2 to be strictly less than at plus n. And of course, at plus n is greater than n by this condition. And then once we get there, the trailing answer actually just equals at, and we can break. And what's that? Wait, so when would at equals 0? So at there's just make it an explicit condition. Yeah, so M2 is going to be so if M2 is strictly less than n, then this is like a vacuous condition. Let's put it here. If M2 is less than n, then trailing answer equals 0, because you don't quite get there. And I can break. Four, 0, 0. So it's sort of right. Sort of, I guess. So why is it wrong on 4, 6? So in 4, 6. Wait, well, shouldn't it have a leading answer? Maybe I'm not computing M1 correctly? So what should maybe this should be n minus 1. So let me think. So 4 is 1, 0, 0. So it has 3 digits. 6 is 6 is 1, 1, 0. So what should happen? M2 should be 1, 1, 0. And then the answer should be 3. So yeah, the right answer is 1. So M2 is 1, 1, 0. So this condition won't be satisfied. And we start at 1. So 6 is not less than Let me make sure I'm computing M1 and M2 correctly. So in this case, there's no leading digits. There's just the trailing digits, 6. And then iterate through here and I try to find the first. Okay, so there's. Okay, so n is 3. There are 3 digits, so I go from 1 bit shift 0, 1, 2, and I see if m2 is less than at plus n. Oh, yeah, I guess something is suspicious with my method here, because I could never give an answer like 3. I can only give answers that are powers of 2, which are incorrect. Okay, so if m2 is less than n, then trailing answer equals 0. Oh, so this condition must never be satisfied. So m2 is 6, n is 4. At should get as large as 4, right? Oh, but when it does get as large as 4, it is contained in n. I guess I see the problem here. I guess the problem is something like yeah, I thought for some reason it had to be a power of 2, but I guess it doesn't necessarily have to be. So what would need to happen for us to have gotten 3? So actually what we're looking for is not the smallest 2k not in n, but the smallest number. So the smallest number that lives in the complement of n, such that n plus that number is greater than m2. Okay. So So the smallest number that lives in the complement of n, and such that n plus that number is greater than m2. So I guess we should so we've got some number n, n1 to n, and let's say we get to 0 somewhere. So the sooner that we get to a 0, the less we want to add it, because if we the sooner we add numbers, the bigger they get. So we want to. So I guess the question is, do we need to add this number? So if so let's say this is at k. So if n1 to nk minus 1, 0, all ones is less than or equal to M2, then we have to add it. Otherwise, no. Okay. So I guess this is sort of like what I was trying to do originally. Going in circles now. Okay, so... Okay, so now let's start at the end. So start at n minus 1, go to 0. So we just need to ask, do we need to add this number? So if say if M2 is less than n, then we're just done. Let's just print M1 and continue. Otherwise, let's do this thing. So if M2 is greater than n, okay, then we do this thing. So this is where we're at. And let's just do this comparison. So if okay, so what is this number? It's our number n bitwise ANDed with this thing. It's gonna be hard to write. So the first, okay, so we're at, let me just name this. Okay. Okay, so it's always going to start as 1. So let's just like first. I'll just name it first k. Yeah, that's going to be 0. And at the end of it, let's just say first k plus equals at. And what do we want to see? We want to see if n XORed, or so n ANDed with the first k. So in the beginning this is 0, but afterwards it'll be the first k minus 1 digits plus at minus 1. So that's the number that is 0 and then all ones. So if this is still less than or equal to M2, then we have no choice but to add it. And then we don't need this check, we don't need this check, and okay. Let's see if that works. I'm printing some things I don't need to print, I think. Just delete that. $470. Okay. 640. Ooh. Okay, wait. I think this is progress. We just need to figure out what's wrong with 7. So this should be 3. So somehow it's adding the first one. Oh, so I do not want to add it if it's already in n. Right? That's what I wrote down. Where's my so yeah, smallest number not in n. So I want this condition, but I also want at and n to equal 0. Where am I? 430 640 531 903. What? No. Oh dear. I thought I was right there. 531 903. Okay. Might be helpful to look at the binary expansion of these numbers. M2 is less than n. What are we getting in? We're getting these two numbers in. Okay. 1, 2, 3, 4, 5, 6, and okay. I'll just get a binary calculator. I guess that's what I should do. Wait, I wonder if Python can do it. Python print bit string number. I'm sure it can. I just don't know how. Okay. Bin. Okay. Okay. 1, 2, 3, 4, 5, 6. 6, 5, 4, 3, 2, 1. Oh, it's just the digits backwards. I thought something else. Okay. Again, then I thought the answer was 531903. When in fact the answer was 530866. Okay, so my answer differs from the correct answer in a few places. Okay. This is not very helpful, actually. This is not helping me understand at all. Okay, so what was I thinking? I was thinking that we do get to 0 because m2 gets to n, and then we want to find the smallest number that we don't quite get to. And what would cause us to not get to a number? We would not. Okay, so we want to kill. Okay, so we want to kill as much as possible, and we can kill everything. We know that. And then we want the smallest number. So if we're trying to minimize the number we get, so we start with this we start this bit string n1 to nn, and we want to find the number that XORs with this to the smallest number that is this is very confusing. Okay, so we get to 0 when we get to m equals n1 to nn, and then the question is just like, what number have we not gotten to? So we let's give us an explicit example, which I guess we have down below. So we're let's not use that example. Okay, so like 1 1 0 1 1 1, and okay, so m is greater than, or so m2 is greater than n. So we know we can kill everything. And then I guess the question is, so if m goes all the way up, then we know that we see every number, because like in particular m equals 1,000 works. So we see the all ones vector, but we see every other number. So I guess the question is, what is the smallest number we don't see? I guess we actually want to kill the things inside n, not the things outside of n. So like if this is I guess we want to find the smallest number we do have. This is tripping me up. So we're just not getting this last test case. And the correct answer is 0866. Yeah, I guess it makes sense that they have the same trailing or leading digits, because we take the same leading digits in binary. Okay, so where do they differ? They differ here and at these two spots. So notably, the correct answer is smaller than our answer. Okay, so the final number we give lives inside n, but does their final answer live inside n? I mean, or our final answer lives outside of n. Is that where it should live? So this is 6. Okay, so, yeah, so let's go back to the beginning. So we know we get 0 if you get to n, and we know you don't get to 0 if you're less than n. If you do get to n, how do we know if you get to 1? You get to 1. Have we already gotten 1? We've already gotten 1 if n doesn't have a 1 in the last digit. If it does have a 1 in the last digit, or if it does not have a 1 in the last digit, then you get to 1 if m2 is n plus 1. So thinking about that, I thought the right answer would be to find the smallest number that lives in the complement of n that we actually reach. Because there's like two things going on. We need to reach it, but so we have 7 minutes or 11 minutes. Gotta get it quick. Okay, so this condition is asking, do we reach m2? But I guess it's not really asking if we reach m2, because maybe maybe comparing to m2 is not the right thing to compare to. Oh, you know what? I think I need to add first k to this. Maybe. First, oh. Is that the same answer? It is the same answer. Actually, the fact that it didn't change any of the answers makes me think that there's probably something wrong. Oh, wait. What the heck? This doesn't make any sense. Oh, wait, I wanted to add trailing answer. What I've already added, essentially. Okay, well now it's changing answers. It's still not the right answer. Let's see what that one looks like in binary. I don't know if it'll help us. It probably won't. Whatever. Okay, so how did it change? So this was our original guess to the answer, and now it's not really adding any ones anymore. Interesting. Wait, why did I think I should add trailing answer there? Okay, so I want to kill everything I can kill, and I know I can kill everything in n because m gets to n. So I want m to get up to n, and then I want to like choose m plus some other number that maximizes what it kills with n. Or I want the number that I cannot get to. So I want to kill everything, and then I want to like find the smallest number that I don't quite oh, okay, so I want this. So I want the smallest number that lives in n such that n plus that number is greater than m2. Okay. So m2 minus n. Yeah, so I want number to live in n and be greater than m2 minus n. So I'm computing that number, and I'm seeing if I should add this to it. So I do need it to live in n, and I also want it to be the case that that I need to add it. And how do I check if I need to add it? I need to add it if what I've added so far plus the leading digits of n plus adding everything else still less than or equal to m2, then I need to add it. And so what's wrong? That seems like correct. Let me make sure first k is right. Oh right, I forgot that this is going to look like like this. But I don't know. Who could tell if this is right? I guess I can just like actually compute them. So I guess they should look like a bunch of leading zeros. 131008. Yeah, they look like a bunch of leading zeros. And then what's the previous one in the sequence? 130944. Okay, yeah, that looks like that's right. So in first case starts at 0, so I haven't added, n doesn't contribute anything. I just have, and this is also 0. So it's just a question of whether at -1 is less than or equal to m2. And if it is less than or equal to, yeah. So if I don't add it and I only add what remains, then of course I'm gonna need to add it. And now I want it to live in the complement of n. Try and answer plus equals that. Am I going as far as I need to? The fact that it works for the small numbers makes me think I am. So I guess I need to start with, so if n is 1 digit, then this starts at 0, and 1 bit shift 0 is 1, so yeah, it seems correct. There's just a question of whether I... Wait, let me... Damn. Huh. Yeah, I guess I just don't know why it's wrong. That's sort of a bummer. It should be at -1 because I want to add everything else ones. And I want it to be... And if it's less than M2, then that means I have to add it because I won't reach it. So at the end, I should get the smallest number greater than M2 because I kept adding where I was at. And it should be contained in the complement of n. Yeah, I don't know. Maybe I should have looked more carefully at these binary strings. Maybe they would have contained the secret. Yeah, because I guess actually my answer looks quite a bit different from the answer they give. It's like different in multiple places. Yeah, I guess I won't figure it out in the last minute. So their number is smaller than my number, so... Oh! Oh, I think the problem is... or how do I put this? I guess sometimes... I guess sometimes you want to subtract something from M instead of adding something to M. Oh yeah, so my answer is always going to add something to M, but actually that's not what you want to do. Sometimes you do to like... Yeah, I guess there are actually numbers less than n that you won't reach in general. Yeah, and... So you'll always... Yeah. Oh, yeah, I guess you want to, like... No, I don't know. I don't know what I'm getting at. Huh, I didn't think it was that complicated of a problem, but I guess I should have thought more before I started coding or something. Maybe I should have read the other problems. Let's see where we ended up. 2000th. Good start, but 2000th out of... Has 14,000 people to submit? Not the worst, but not the best either. Yeah, I didn't even read D or E. I wonder if they all have sequences of integers. We're given an integer n, find any string s of length n containing only English lowercase letters, such as each non-empty substring of s occurs an odd number of times. It's interesting. So I guess like the first observation is every character has to appear an odd number of times. But if you just like have a string of all a's for an odd length string, then you'll have like n choose 2. Or a substring, I guess. Okay, so yeah, you'll have Yeah, you'll and choose 2 substrings of like all A's, but wait, how is this possible? You can't have like if you have 3 A's, then aren't there 6 substrings that are AA? Oh, beginning and end. Okay, okay. Right. So there's only one that's AA. Okay, so you can never have a run of 3 characters. You can have a run of 2 characters, but if you do have a run of... Wait, here there's... Oh, so you can have a run of 3 B's, but then you have to have BB somewhere else in your string. Okay, interesting problem. Definitely seems harder than C. I guess I'll read E as well. U. Whoa. Wait. Oh, okay. They're like doing the automated grading, so this is like not a representative of how many people actually submitted correct solutions. Yeah. Second, I was confused. We're given n nodes, and then we have a sequence of integers. We want to perform the following operation n times. Select an unerased node. Yeah. Then erase it in all its edges. And then we want to find the number of... So the number of different sequences such that we can obtain A by performing this n times, and the GCD. Okay, I don't really want to think about it actually. It does look hard though. Okay, well I guess it's an okay showing for the first time back though. I would have really liked to get C. Alright, thanks everyone for watching. It was a lot of fun.